We also talked about recursion last time, right? So what is recursion all about? So it's about defining objects in terms of themselves, right? That's what the recursive definition is. So today, what we'll do is we'll have a bunch of recursive definitions. We'll talk about defining sequences, the same thing as functions, defining them recursively. We want to define sets recursively. And then with those recursive definitions in place, we want to prove certain facts about those recursively defined structures. But when I say structures, I mean sequences, functions, or sets. So these are three kinds of object that we'll be dealing with today. Okay, so you should see my full screen here. Okay, so powers of two. You have a definition of the powers of two. What do we mean by this? Well, it is a function. In what sense is this a function? It is a mapping. This f that we use normally for mappings from one set to another set. Okay, this is our representation of a mapping. Okay, these, let's take the one function just as an example. So f of n, it's just another, this a sub n, it's just another customary definition for f of n. This one says that take any number from this set here, from non-negative integers, any number here, and apply to it this function f, okay? Or apply this, it's a function, if you will, just written down slightly differently. It's just a matter of notation. Okay, a of n is 2 to the n. This is an explicit definition of the sequence itself, of the mapping of the function itself. Okay, so in this example, 0 goes to 1, 1 goes to 2, 2 goes to 4, and so on. Okay, 10 goes to 1024, and so on and so forth. So every integer, every non-negative integer has some image. That is a mapping from one set into another set. This structure, again, I'm using the term structure, but this function, let's call it this mapping or this sequence, can be defined recursively. What would be a recursive definition of this? Well, recursive definitions have two pieces to them. They have a basis step and they have a recursive, what's called a recursive step. The basis step of the definition is specify the value of this function at some particular point. In this case, we're defining the values of the function over a set of non-negative integers, and our starting point is going to be the 0. Okay, so we'll specify the value of this function at 0. Okay, what is the value of this function at 0? I'm going to say that a of 0, which is the value of my function, this is just extra piece of notation. You really don't have to use this one, but just to underscore the fact that this is a mapping. The value of this function at 0 is going to be 1. Okay, that's our definition. And then we have what's called the recursive step. The recursive step of the definition generates a new object, a new element from the set of elements that can be generated by the recursive definition based on the elements that already exist in the set. Okay, I want to define the value of the function at point n plus 1 in terms of what I already have. Well, f at the point of n plus 1 is going to be, in our alternative definition, this is the n plus first element of the sequence. Okay, by the recursive definition, that element is twice whatever the value of the function was at a previous point. So it's twice a sub n. That's the recursive definition. This is called the recursive or an inductive definition. So why is it the same as that one? Just make sure it's clear before we move on. Well, a sub 0, that is, 2 to the 0, that's 1. A sub 1, that's going to be 2. 2 to the 1, that's 2. That's 2 to the 0, that's 1. A sub 3, whether I plug it into this formula, on the one hand, this is 2 to the 1. On the other hand, this equals a sub 2 times 2. So on the one hand, so on the one hand, so this is a sub 1 times 2. This is 2 to the 1. 2 to the 1. This is 2 to the 0. This is, by definition, just a sub 0 equals 1. We defined it that way. A sub 1 is going to be whatever you had before times 2. Whatever you had before times 2. This is a sub 2. So you can plug it in, you get a 4. You can plug this in, you get a 4. This is an alternative definition. What is the third term according to the explicit definition. Just make sure this is clear. These are alternative definitions. If you, the familiar definition, which is the explicit definition, you may be more comfortable with as of now, but there is no need to be more comfortable with this than with the recursive definition. That's just simply you plug it in, you get the answer. In the recursive definition, A sub 3 is defined in terms of the previous term. And of course, the answer should be the same. Okay, one more term, A4. It's A3 times 2, according to the definition that is recursive definition, or explicit definition simply gives you the definition, and so on. So A sub 10 is going to be 2 to the 10. That will give you 1024 if you use the calculator to plug it in. Or it is the same as A sub 9 times 2, okay, which is 512 times 2. How do I know it's 512? Because I knew all the terms that came before, okay, and so on. Okay, that's also 1024. This is what a recursive definition is all about. This is a recursively defined function. Any questions about this so far? Okay, so again, this is just a summary, this slide, a summary of what I've just said. Explicit definition versus recursive definition. And what's coming next is that once we have these recursive definitions in place, we can use mathematical induction to easily prove some results. So we'll see about the recursively defined structures, and we'll see how natural that connection is between induction and recursive definitions. Okay, quick example. F of 0 is 3. This is a recursively defined function. Okay, so recurrences are defined this way. F of n plus 1 is defined in terms of the previous term. Okay, so what's f of 1 then? Well, whatever the previous term, it says whatever the previous term was, which is 3. Yeah, you just, that's the rule that gives you the next term. So that happens to be, okay, this is probably 9. Then you have f of 2. It says just multiply the previous term, this is the point, previous term, and then do something to it, linearly transform it. Well, it's going to be 2 times 9 plus 3. I think that's 21, and so on. So you get the idea. F of 3, what is it? Well, you take the previous term, f of 2, whatever that was, and do this to it, multiply it by twice, and add 3 to it. Okay, so it's going to be 2 times 21 plus 3, 45, and so on. So you get the idea. Okay, so that's a recursively defined function. You can compute any value of this, the value of this function at any integer if you have this recursive rule, 3, and the basis case, of course. Okay, so now my question to you. You're familiar with n factorial. When you first saw it, somebody tells you, oh, that's just the product of numbers from 1 up to like blah, 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 up to n. They told you about this blah, blah, blah. Okay, and you said, okay, so no problem. No, I get it. You take any n, you plug in any n into this formula. This is f of n. This is just another notation of f of n. This is a function. It is a function. It takes in an integer and it produces some integer as its output. That output integer happens to be the product of the first n integers. Okay, but it's a function. Okay, so what's the recursive definition of this function? So what do I have to do to define it recursively? I need a base case, right? I need a base case. What's my base case? Let's start at, well, I should really start at 0, but fine, let's start at 1. Okay, 0 factorial is defined in 1. It makes great sense in combinatorics to define 0 factorial as 1. You may have seen this in either discrete probability or combinatorics class or 1166, whatever. But anyway, here, let's start by 1. We don't want those subtle points here. Define it as 1. What is the recursive step? I want the value of the function at some point in terms of something, some rule that involves f of n. So what is that rule? So help me out, please. I'm stuck. Does the recursive definition make sense to people? Everyone? Okay. All right. So help me out what the rule is then, please.
Part of the rule involves multiplying f of n.
With what?
Mm,
By n plus 1?
yes.
Okay, yeah, that's exactly right. Okay, so let's see that that makes sense. Okay, so here's my, okay, f of 1. Well, that's by definition 1. It's 1. Okay, here I'm going to have recursive. Here I'm going to have explicit definition, recursive definition. F of 2. Recursive says multiply 1 by 2. Explicit says also multiply 1 by 2. Okay, so I have the answer. This is 2. F of 3 says, okay, so just to be clear, we can distinguish between 2. F of 1, that is 1 times 2, that's 2. This one says it's 1 times 2 times 3. That's my n factorial explicit definition. The blah, blah, blah definition that we talked about. Oops. That definition. Okay, what does the recursive step say? It says, oh, what am I saying? Nobody stopped me. 3 times f of 2. That's what the explicit definition says. It's going to be 3 times 2. It's going to be 6. Well, that happens to be 6 too. What is f of 4? People get a hang of this, right? This is like pretty straightforward, right? You just want to make sure that we do it. What is the recursive definition? 4 times, what should I write here? This is how, if you wrote the recursive version of this, if you wrote the iterative version, you may have done something like this, computed this, okay? That's still 24, and so on. So let's do one more and leave it. It's going to be 5 times f of on the previous. So I'm using this formula every time in the recursive line there in the bottom. I'm simply applying this rule. This one is a rule, and this one is an explicit formula. That's the difference. Okay, so this one says it's 5 times f of 4, which is 5 times 24. That works out to 120. And that is 1 times 2 times 3 times 4 times 5. That's also 120, of course. Either rule, either the rule or the explicit formula give you the same result. Okay, so I won't do any more. Okay, so, all right, any questions about this? This is a recursively defined function. Recursively defined function. One more example, fine. Aliens descend onto planet Earth and they want to know.
1 second.
Yes.
Can you scroll back up? I just want to take a picture because I didn't finish copying.
Okay.
Sorry.
Yes.
Thank you. Okay, you're good. Thank you.
Okay. Any questions about this? Just tell me if it's fast or slow or whatever. Okay. So that's the recursive definition. Now, the story is that the aliens show up at your doorstep. They knock on your door. You open up. And they say, look, can you help me out? You have this symbol in your civilization. It's called the sum. It comes from the Greeks, sigma. That's so you have this for over 2,500 years. I'd like the definition of this. If you explain what that is. And you decide to give them a recursive definition. So you define, okay, so it's clear what that means, right? So suppose you have A0 is like 7, A1 is 9, A2 is 11, and so on and so forth. A3 is like maybe 13, and so on. If you say something like k equals 0 to 3 of a sub k, you're saying A0 plus A1 plus A2 plus A3. You have these 4 terms. So that's going to be 7 plus 9 plus 11 plus 13. And if I'm not mistaken, that's going to be 16 and 11. That's 27. That's 40, I think. It doesn't matter what it is. The point is I'm summing up these numbers here. So now you help me out. Now it's clear what a recursive definition is. I want to define this recursively. Okay, so it's clear. This is the way you've understood the symbol, and there's no question about this. I'm not questioning this at all, but would like an explicit definition. So recursive definition is to give a basis case, of course, basis case, and then to give an inductive step, recursive step of the definition, rather, recursive step of the definition. The basis case says, so first of all, what is it a function of? We should write it down more clearly. So what is it? So we're defining a function. How is this a function? Of what argument? Help me out. Can you help me out? Like, I'm stuck here. K equals 0. This K is just an index. So n, I think it's a function of n. This is a function of n, right? You change n, you'll get a different sum. You know, whatever the terms are, of course, it depends on what the terms are. But the argument here is this n here. So in the basis case, I'm defining it for n equals 0. Just the basis corresponds to the inductive, to the basis step of the inductive definitions. You see the correspondence now. We'll make a closer connection in a minute, more precise, make it more precise. So I'm defining f of 0 of this function. That is, I'm defining this thing. This, by definition, is simply the first term of the sequence. That's the basis case. The basis case just defines the value of the function at 0. Now, the value of the function at n plus 1 is going to be the value of this function at f of n, so we'll just be more explicit. This is how we're defining f of n plus a sub n plus 1. That's our recursive. There should be an e here too. That's our recursive definition. Okay. Okay, let's make sure that this definition makes sense to the aliens. What they will do is they have computing power, presumably, and for them to compute a sub f of 15, they will have computed by then f of 14. So let's plug it in. Well, f of 0, here's f of 0. Well, that's going to be a0, whatever the first term of the sequence is, right? That's a of 0. Okay, f of 1 is going to be a of 0, which was, well, let's write it. So here I'm going to have recursive. So this is going to be recursive definition here. So what am I writing here? Well, I look at my rule and it says, take whatever the previous term was and add the next term to it. So, okay, f of 2 is whatever the previous term was, f of 1, and add a sub 2 to it. No problem. One more term. F of 3 is going to be whatever f of 2 was, plus another term added to it. So what does it work out to? Well, f of 0 was a0, so that's going to be a0 plus a1. This is going to be f of 1 was a0 plus f1. A1 plus a2. This one, whatever f2 was, which was a0 plus a1 plus a2 plus a3, and so on. So I won't write down the 15th term. But that gives a recursive definition of this symbol. The symbol stands for f itself. So f, this vaguely corresponds to this symbol in this context. It's a generic symbol f. Here's f has a concrete meaning. It's denoted as sigma, and that stands for the sum. Okay, any questions about this? Okay, that's clear. But we can also define sets recursively. Okay, so well, what does it mean to define a set recursively? Okay, specify in the basis step that some guys like this guy, that guy, and that guy over there, they all belong to this set. So you specify the initial set of elements. And then you give a rule again, or a few rules, of how to generate new elements of the set. That's a recursive definition. That's a recursively defined set. An example is coming in a minute, and we'll actually do quite a few examples in the recursively generated sets and prove results about them. Now, there's one assumption that's usually made. The set consists of anything that's generated, of everything that's generated by these rules, and nothing else. Okay, it's sometimes called exclusivity property. Here's an example of a recursively defined set. Let S be a subset of the set of integers now. So we have a set of integers, and we're specifying its subset. And the subset is defined in the following way. Well, in the basis step, I specify that 3 belongs. Okay, so 3 is in this set. Okay, all right, so 3 is one element of the set. Fine. The recursive step gives me a rule. If I have two elements that I know to be in the set already, like x and y, then their sum is also in S. Okay, so basis step, so let's see what elements are in it. Okay, first of all, 3 is in it because by the basis step, that's in it. You also have, well, okay, so what does the recursive step generate for me then? Okay, it says, well, here's a 3, here's another replica of 3. I know that 3 is an element of the set. I'm also told then that 6 is also element of the set by recursive rule, by the recursive rule, by one application of the recursive rule. I get that this is there. Okay, what else is there? Second application of recursive rule. What do I get? Okay, what elements can I generate now?
Multiples of 3.
What do you mean by multiples of 3? That will end up to be indeed the case. So you're answering the question I was about to ask in like 2 questions from now. But I've asked a very particular question here. In the second application of the recursive rule, okay, that's a correct answer to a different question. Okay, but can we see what's here? Like I'm applying now. So far I have just 2 elements. I've determined that I have 2 elements. So far, I know that 3 and 6 belong are the elements of S. That's the only thing that I know. There's no way to claim that the number 21 is here in this set S. Although you're correct, it will end up being there if I apply the recursive rule sufficient number of times. Okay, sufficient number of times. So far I know that 3 and 6 are in S. So by the recursive step, what do I have? 3 plus 3 is there. I can take over, but I know that 6 was already there, so that's not interesting to me. 6 is here. 3 plus 6 is here, is in S. So let's just simply write, to save some space, say is in S, is in S. 6 plus 3 is in S, is in S. 6 plus 6 is in S. Okay, so I've generated some new elements here. 6 I knew was there, but I have 9 and 12. Okay, so by the next time, by the next application of the recursive rule, we know that 3, 6, 9, and 12 are in S, are in the set S. So now I have 4 elements. Then I look at their sums. They're going to be there, and so on and so forth, right? Okay, so now you've already answered the question that I'm about to ask now. Can you guess what exactly will be there? And you made an excellent guess. And that guess was that this rule generates all multiples of 3, and more than that, nothing other than the multiples of 3. So anything generated by this rule is a multiple of 3, and every multiple of 3 is in this set S. Okay, these are 2 things that we need to prove. And we'll prove them in a second. But now, well, before we prove this, first of all, let's skip the strings. We'll have a separate section on computation, the foundations of computation. So to the extent that you need it for a couple of questions in the homework assignment, yes, please do it and ask me questions about it. But I will not ask you about strings on the quiz. I want to skip that for now. we want to prove some results. First of all, I want to prove your guess here. Okay, set of all positive integers that are multiples of 3 is what S is. And I'll prove that maybe by the end of this class if we had time. We didn't have time for this in the other section for some reason. So just to keep things synchronized, I want to define something else for now, recursively again, so that we can prove something of substance by the end of the day. I'd like to define something called an extended rooted tree. Okay, so in a couple of classes from now, we'll start talking about graphs. We'll see that the graph is a structure that consists of something called dots. Okay, so we'll call them dots, but these are really more often called either nodes or vertices. And special pairs of them are selected, and the selected pairs are usually denoted by connecting them with what's called an edge between them. It's simply a line between two dots called an edge that simply designates that pair as special somehow in this graph. Okay, so here's an example of a graph, a bunch of dots, some pairs of which are connected by these lines that we call edges. That's all there is to a graph. Okay, turns out to be quite useful in many applications. And later I will be asking you questions like how many edges, what is the maximum number of edges that you can have in a graph that is defined in a special way. So for example, here in this graph, okay, you have n vertices, in this case 6 vertices, and every pair of 6 of the 6 vertices, every pair of them is connected by an edge. So how many edges can you have in a graph like this, where n is not necessarily 6? Here you obviously can count the number of edges. But if n were something like 25, how many edges would you have in a graph like this? We'll later call this a complete graph on 6 vertices and have a special notation for it, but that's coming in a couple of lectures from now. For now, we're going to be interested in a very special case of a graph called a tree. So on the right side, you see a bunch of trees. Okay, some of these are what's called binary trees. Okay, so this is a binary tree. This one is not. This one is not a binary tree, and so on and so forth. So we'd like to define what a binary tree is. In fact, we'll define what a full binary tree is and what an extended binary tree is. Okay, and before then, we'll just give a general definition of a rooted binary tree. So let's take a look at what that is. So I'd like to give a definition of a rooted binary tree. So here's the definition. And it's going to be a recursive definition. Okay. So in this recursive definition, okay, so we're defining a set recursively, set of rooted trees. In the basis step, I have to specify an object that belongs in this set. I'm going to say a single dot or a single vertex. Let's call it vertex because that's the terminology that we'll use instead of the node, or even we can say node, it doesn't matter. Nobody uses dot, but you scatter dots on the plane or not necessarily on the plane. And those are vertices. As far as your representation is concerned, that's it. A single vertex, okay, denote this by R. Call this R, single vertex R, just to have a name for it, is a set that I'm trying to define, is a rooted tree. Rooted tree. Okay, so this is what I'm defining. So I'm just put one element into that set. That definitely belongs there. Then I'm giving a rule. What rule would generate new rooted trees? And here's the rule. Suppose that T1, T2, sub T3, blah, blah, blah. Somehow I know that these objects are rooted trees. Let's call them disjoint. They have nothing in common. Disjoint rooted trees. Trees with roots R1, just to have names for them. This is R3 and so on. With roots R3, respectively. Okay. If I know that these trees here, this trees, should we give them a different color? T1. Yeah, let's use a different color. These are known, these objects are known to belong there. Okay, so R belongs there. Then I can construct a new object by specifying a new, so then rule. Take a, okay, so basically vertex R is a rooted tree, and we'll call this a root, okay, a root of that tree, called a root. Take a new root, that is, take some vertex, just call it root now, take a new vertex R, which will be the root of the tree that we're constructing, which will be the root of the tree we're building. We are building. Okay, take a new vertex R and connect, okay, and connect R to each one of these trees, T1, T2, T3, T4, dot, 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 whatever. Okay, so as many trees as you'd like. Okay, so just to write it down in words, root of the tree, take a new R and connect R to the roots of T1, T1, T2, T3, etc., etc. So here, these are these roots that we had before. These roots are here, okay? R1, R2, R3, and so on. And these are trees. There's some structures. I don't know what they look like, but I know they're disjoint, but I know them to be already elements in the set that I am about to define. I have defined. You know, this may seem like a strange definition. I'm defining something in terms of itself, but it's not that strange. So let's see exactly what's generated by this definition. Like, is this definition clear? Okay, so let's see. First of all, what is the basis step? Generates what? By definition, the basis step generates, so basis step generates just one element, generates just one rooted tree, R. Let's call it R. Okay, that's what I have, that's R. What is generated in the second step? It says, take a bunch of trees that you already know to be in your set, and the only kinds of trees I know to be in my set are just other roots. There are other just dots. So you take a dot and connect it to the new root. So this is new R, new R. You take this new R, maybe connect 2 of them. Those are going to be there. Maybe connect 3 of them, okay? And so on. So notice that at this stage, I have already been able to generate an infinite number of trees, okay? You see? I can connect like 57 of those. Now, what can I generate on the second step? Okay, these are now my trees. So these guys now, okay, so these guys now are my, for the next step, these are going to be like some T1, T2. I can enumerate them if I like. You can give them different names, but these are some trees, okay? Now, what do I get to generate, and so on? What do I get to generate at this step? Well, I have a recursive rule. It takes, take a new R, then take any of these new, any of these elements that you know to already have. For example, take T2 and maybe take another R here, which know to be in your, set, and connect them with a dot. So connect them to this. So basically you're connecting, my T2 was something like that from before, that's T2, and then this R. So this structure here has to be in this set, okay? Okay, maybe I have another one here. Maybe I just have one. So this structure has to be in this set, right? Something like that. Something like that has to be in this set. Something like that has to be in this set. Something like that has to be in this set, and so on and so forth, right? So all I'm doing is taking what I already know to have in this set For example, this guy, I know it's here because it's right T3. This is my T3. This one, I know that way. I called that T2 on the previous step. This one is also T2. So I take any one of them that I'd like, and I take a new root here and just connect them to the roots of T1, T2, and T3. And that's it. That's the only rule that I need to generate these trees. Okay, these are called rooted trees. So we just defined rooted trees. Okay, that's it. That's the definition of a tree. Now, okay, any questions about this? Now notice one thing as we continue, we'll give two more recursive definitions. And the thing to pay attention to is how subtle changes in the wording of the basis step or of the recursive step that generates new elements from what's already known. The subtle changes in the wording of those makes quite a bit of difference of what can be generated. When I draw the trees the next time from the next example, those will look very, very different. So let me give you another definition then. This new definition will be that of an extended, what we'll call binary trees. So what we need now is we want to define two special cases of rooted trees. So binary trees are special cases of those, and we'll have full binary trees and extended binary trees. Let's start from here. Okay, I already copied the definition so I don't have to type, but let me tell you what it is. I need to print to. So an extended binary tree, so again, I'm defining a set of objects and I'm defining it recursively. Now I'm saying that an empty set, so let's denote it by that. That just simply means that I cannot be drawing dots and lines on the piece of paper. This is, okay, is a extended binary tree. Okay, so that just by the basis step. Basis step tells me that. Okay, just simply says that. Now the recursive step. Okay, notice that it distinguishes between something it calls a left subtree and a right subtree. So recursive step generates these guys. Okay. Again, I'm taking this time only two of the elements that have been generated so far that I know to be in this set, and I just give them this designation. One of those guys I call a left tree, and the other guy I call a right tree, and I'm building a new tree that I, call this. Okay, I could have called this T17 or Joey or anything else, but this the third tree that I'm building right now, I'm giving it a special notation just to stress the fact that this T1 stands to the left of T2. Okay, this just is a notation and nothing else. It just stands for some tree. And this is built by taking a root, okay? And then this T1, whatever that object was here, okay, with its root, that had a root. And so that R1, and that T2, which had its own root, R2, that's that. So I don't know what T1 and T2 look like, but this object that I've just constructed according to this rule, I'm going to call this, the name of this object is going to be T1, T2. Okay, you could have named it Joey, but it's T1, T2. It's just a convenient notation for it. Now let's see exactly what kind. Yes, please.
Is that T1 times T2, or is it just?
It's a dot, so it's you can omit the dot if you'd like.
Okay.
It's something that says simply to reflect the fact that T1 stands to the left of T2.
Can you do an example with numbers?
Numbers. Okay, so there are no numbers. So we'll draw this. We'll draw these guys. So yes, we'll do an example right now. In fact, all right. So on the basis step generates just nothing. So on the basis step, it just tells me that I have nothing. Now let's take the first application. So first application. So here's the definition. So actually, let me see if I can copy and paste it while we're drawing the trees. That would be super helpful, I think. So let's do that. Copy, or right, take a screenshot. Okay, and let me put this here and make it smaller, maybe a little bit, just so that you see. So the basis step generated this this empty tree. First application. Now I want to do the first application of the recursive step, this guy, the recursive step. Okay, what do I get during the first application of the recursive step? It just says take a root. So all I get to do here is take something called an R, okay, during the first application. So the only thing that I can place there is going to be a dot, okay, this is called R, and that's it during the first application of it. I have nothing to connect it to, because unless these guys are empty, are non-empty, I can't connect it to anything. But now at the second application, so second application of the recursive step gives me the following. Well, I already have an R. Well, I'm taking a new R, but I already have this dot that I know to be an element of this set that I'm constructing the elements of. So I can connect this R here. Okay, so this dot now is a tree. In fact, I can connect two of them. Or I also know that an empty set is also a tree that I've constructed. So I can have the left subtree of it to be a dot and the right subtree of this R to be nothing, an empty set. And because it's nothing, I'm not connecting it with a branch. Okay. Or I can take an R and have its left subtree be nothing or an empty set and the right subtree be something. In fact, these are the only elements, new elements, that can be generated by the second application of the recursive step. So let's take a look at the third application. So does that make sense? So third application of the recursive step. Okay. Oops. Is there an undo? You guys see what I just did? Okay. Try to save time, and you do not always do. Okay, so how about the third application of the recursive step? What happens then? Well, I already have 4 elements in my set already. So these are the empty set, that's 1, this guy, and then these guy. Okay, 5 elements, sorry, in this set. So to construct new elements, I get to take a new root, my new R, and then take any 2 of these 5. Okay, how many ways are there of choosing 2 elements out of 5? Okay, I will ask you that later, but you will tell me it's 5, choose 2. Okay, but then I get to put each one of them on either side. It's either left subtree or a right subtree, right? So let's just list a few of them, right? Because you're going to have 20 of them. So let's just, I'll let you count these later. But so here I have these root, this root. And then the left side, let's pick this number 3, for example, number 3. So on the left side, I can have such a structure because I know this to be an element of the set. And on the right side, I can have another such structure. This time, let's pick number 4. Okay, this guy. So I can have this here. So that's one of those elements that is generated in the third step. Does that make sense? Or I can take R. I can take R. And I can, on the left side, let's just make this time an empty set here. There's nothing on the left side. Right? There's nothing on the left side. On this side, I can make these guys, like this guy and this guy can generate, for example. That was the 3. And I have a bunch of others, like I can have this is one option. This is another option. And I'll let you count all of them, okay? This is another option, and so on and so forth. But you get the idea, the kinds of structures that I'm being able to generate with this definition. Now, notice that I have nothing like these guys that I drew there, like nothing like this kind of thing. I don't have 4 branches emanating from any of these nodes, any of these dots. At most, I have 2. Okay, at most I have 2. I can have 1 or 2 or none. Now let me define, okay, so is this clear? Is this clear what I'm doing? It's just a recursive definition. It takes a minute to get a hang of it. You have to read it maybe several times. But let's define one more recursive structure and then actually start proving something about these trees. Now I want to define something called a full binary tree. Now a full binary, notice how subtle the difference is from, see if I can place these side by side. Let me see if I can get this extended binary tree definition so that you see the difference, right? This guy. And now I'm defining something else. Okay, I'm defining an extended binary tree. Let's put these guys here. An extended binary tree. Okay, so let's define now full binary trees. This one says, again, notice that first of all, it doesn't say that an empty set is in it, and that this will make a huge difference about what kinds of trees can be generated, what kinds of things you can draw as elements of this set. So this one had an empty set. This one doesn't say anything about the empty set. It says that the basis step now, generates this guy called R. It's a dot. Okay, so I put a dot. But then I have 2 subtrees that I've generated, T1 and T2, whatever those are. Okay, and these 2, okay, T1 and T2, I get to construct a new tree according to a similar rule. I call this new tree is going to be called T1, T2. You can put the dot in between. It doesn't mean multiplication or anything like this. There are no numbers involved, right? It's just a designation. In fact, it's a notation for another tree, okay? Just T1 stands to the left of T2. That's all it's meant to convey. And you get to connect this new root R with T1 and T2. Okay, that is this definition, the recursive step. Okay, let's see what the first application of the recursive step gives. So let's see, what can so you help me out this time. So basis step, I know, so basis step gave me just a dot. So this is the basis step application. So we'll call it an R, but it's a dot. Now I'm applying this definition just once. What can I generate in step 1? I call it step 1. This is step 1. Help me out. Okay, so I know that I have a dot here, and then the only other thing that I have is another dot. I don't have any empty sets. Notice that I'm forced at this step to have both. This is called a full binary tree. I'm forced to have both of these dots here, right? This is my T1 and T2 have no place to go but to be these guys, just the roots generated on the previous step, because the basis step just gave me one element, like just this guy. So that's the only thing I can generate in step 1. How about step 2? Step 2. So that's the second application of the recursive step. Now, what can I generate now at the second application? So I know what do I have so far in my set? I have this guy and I have this guy. I have nothing else. And what does the rule tell me do I get to do? I get to create a new root. This is my new root. And then my T1 and T2, which are left and right subtrees of this root, get to be either one of these 2 objects. So I can have this, oops. I can have this, that's another root, which was generated on the basis step. On the right side, well, I could have another root too, but that's generated on the previous step, so that guy was already generated. On the right side, I can have this entire guy is already an element of the set. So on the right side, I can have this. So that's one structure. that the second application of the recursive step gives me. That's yet another structure. I can have this guy on this side and this guy on this side. That's a different tree, different full binary tree. Or this structure I haven't generated yet. I can have both of these subtrees be those guys, these guys, the guys that were generated in the previous step. Okay, so this is my root R, and then these. So these are full trees. It's like you have. So okay, so what's generated in step 3? Step 3. I get to do a new root, and now I get to put, like, for example, let's put this guy as a subtree. So this is going to look something like that. Let's put as a second one, let's put something like this entire tree here. That's what can be generated at the next step, and so on and so forth. Do people get the idea?
Yes.
Okay, so, or let's draw one more, and maybe we do something like this, okay? And then on this side, okay, maybe we already did that. Okay, and then get a root on this side. That too, right? Okay, because that R was generated at the basis step. So I can take that's already a tree that's there, and this is already a tree that was generated right here. Okay, so those are trees. Those are already all elements in the set. Okay, so you get the idea. So notice that how different these drawings are depending on the definition. So these are subtly 2 different definitions, and the kinds of trees I get to draw. So I think you should do this exercise like on your own also. So just looking at the definition, what kinds of structures you can draw. Okay, so here's the thing. We have, what, about 12 minutes left. I'm not going to do the proofs that I wanted to prove, but we'll certainly introduce 2 more definitions so that we have everything in place then to do the proofs next time. Notice, remember, I hope you didn't forget that I owe you 1 proof, which was your conjecture about our first recursive set definition, where we defined all the multiples of 3 which were there, like this definition here. We want to prove that this set consists of multiples of 3s and nothing else, and all multiples of 3s and nothing else. That's what we want to prove. And we'll prove that next time because we're running out of time now. The way we'll prove it is we'll use mathematical induction. When your sets, like the trees, are defined recursively, you can also use another variant of mathematical induction, which is sometimes referred to as structural induction. Proofs by structural induction have 2 steps, okay? It has the basis step. You get to show that the result holds for all elements that were generated by the basis step of the recursive definition of that step. So for example, with the trees, the basis step here generated roots, okay, these dots. So if I'm carrying out a proof by structural induction, I'm going to have to show that whatever I'm doing, that result that I want to prove holds for that root. Okay, that will be the basis step. And then I want to show, and this is usually done by induction, that whatever is generated by the recursive step, the result also holds for those elements as well. Now, this is abstract, so we want to actually drive this home by giving a couple of proofs. But before we get to the proofs, we need 2 more definitions. I'd like to define what a height of a full binary tree is. Again, height, now notice that what we're doing now, we have a recursively defined structure. That structure is a full binary tree. On that recursively defined structure, now I'm defining, again, recursively, some quantity over it. Now I'm defining a number on top of the structure. That number will be the height of the tree. And here's what it says. Okay, I'm going to copy this. Okay, so here's my height definition. Oops, I don't know what I did right now, but I think, okay, sorry, height definition. So let me draw one of those full binary trees so that people get an idea. Okay, so maybe it looks something like this. Maybe I have a tree that's like this. This is a full binary tree. Okay, so you can verify that the few applications of the recursive step can generate a structure like this. Now, presumably this tree is generated, okay, the last step did what? It created this R here and applied that R to the left subtree, let's call it T1, and to the right subtree. Let's call it T2. Okay, that's just what the recursive definition gave us. Now the height of this, we're going to call this tree T. By the way, this T is T1 and T2, right? We're going to give it a second name, a nickname, T. Now I want to define, okay, defining, let's use a different color, define some number on that tree, h of t. That number is going to be this. The height of t is going to be by 1 bigger than the larger of the heights of the two trees. Okay, notice that I don't know what h1 of t1 is, and I don't know maybe what h2 of t2 is. But whatever it is, the height of the new tree, the guy defined at the recursive step, is going to be 1 higher. Okay, so let's check. On the first step, so what's the height of a root tree? Height of just tree that is just a root. It's going to be 0. Okay, that's a 0. That's the basis step of this definition. That's what it tells me. Now suppose I generate this tree. What's the height of this tree? This green T. So this is my green T. This is T. What's the height? It says 1 plus max of, this is my T1, this is my T2. Max of T1, height of T1, and height of T2. What are the heights of T1 and T2? 0 and 0 by the basis step of the definition. So the answer to this is going to be 1. The height of this tree is 1. Let me give a couple of more examples, and then you'll say, why wouldn't you just simply say that it is the number of branches that are leading from the top of the tree, which we call the root, down to the last, these guys we'll later call the leaves. Okay, so we'll end up with the, once I'm done with this definition, showing you a few examples, you will say, why don't you just simply say it's just the number of branches here? That's the height of the tree, and you'd be right. But we're not saying that, okay, yet. Okay, now here's another thing. Here's the tree. I know that the height of this is 1. I know the height, what's the height of this tree? Now this is my new tree. Height of this T is 1 plus max of T1, T2. Height of T1, height of T1, and height of T2. That's going to be 1 plus max of 1 and 0, because from the previous step, I know that the height of this is 0, the height of this is 1. We just determined it here. So I know the height of that tree to be 1. So that's going to be 2. Notice that's the longest path, and I know I haven't defined the term path, then we need that definition. We'll define it when we get to graphs. The longest, the number of branches, number of edges here, from the root to the farthest down what we'll later call a leaf. These guys are called the leaves. Okay, so 2. What's the height of this tree? Well, if I know that the height of T2, is 3, and if I know that the height of T1 is 1, then height of T is going to be 1 plus max of 3 and 1, which is going to be 1 plus 3, which is 4. Indeed, the height of this tree is going to be 4. You know, the longest path here, or you could have taken this one here. So same root. Okay, the height of this tree is going to be 4. So we've just defined a quantity in terms recursively, in terms of itself. That itself being known on the smaller structures, which structures themselves are recursively defined in terms of themselves. I know it sounds weird, but I hope these definitions make sense. So if you read this chapter, these will make sense. Okay, so I think we should end here. We have 3 minutes.